This continues the lectures on Chapter 3, Two-Dimensional Kinematics. For the remainder of Chapter 3, we take a look at two very important types of motion that occur in two dimensions near the surface of the Earth. The first of those types of motions is referred to as projectile motion. The object itself is called a projectile. Now, neglecting air resistance, very simply a projectile is as follows, like so. What we now seek to describe is the kinematics of a projectile. In order to describe the kinematics of a projectile, however, what we need to know is its acceleration. Because if we know what the direction and magnitude is of the acceleration of a projectile, then in theory, mathematically, everything else can be found out about the object. Its velocity as a function of time and its position as a function of time. So now we start to take a look at the kinematics of a projectile. Okay, so what is a projectile's acceleration? Well, in just a few minutes, I'm going to show you a classic demonstration that illustrates a projectile's acceleration. This demonstration is a demonstration that all introductory physics students see. The demonstration itself has somewhat of a funny name. It's called the monkey hunter demonstration. The monkey hunter demonstration is designed to illustrate the acceleration of a projectile. The demonstration is rather involved. What you are to do is now pause this video and then look at the videos that I've posted for you of the demonstration itself. So go ahead and look at those videos now. Okay, now that you've seen the demonstration performed, explained, and its results shown, now let's go through how the results of the demonstration give us, or illustrate rather, the acceleration of a projectile. Okay, so first of all, let's begin by defining things in the following way. Let's say that right here is the XY plane, the X direction is horizontal, the Y direction is vertical. And then by definition, let's say at the origin here of my coordinate system, that then corresponds to the barrel of the blowgun that I used in the demonstration. This then means that by definition, the initial position of the projectile is going to be equal to 0. We're going to label this as R0 projectile. Okay, and then initially, as the demonstration begins, we have the target, the monkey, up on the ceiling. So then therefore, the initial position vector of the target, the monkey, looks like this. Right here, we're going to label this as R0 monkey. Okay, and then we have the initial velocities of the two objects. The initial velocity of the monkey is equal to 0 because, as you saw, the monkey is dropped from rest. So V0 monkey is equal to 0. Okay, now what about the initial velocity of the projectile? Well, the initial velocity of the projectile is definitely not 0. We don't know what its magnitude is, but we do know its direction. Recall in the demonstration that the barrel of the gun is pointed directly at the target, the monkey up on the ceiling, as the demonstration begins. This then means that the initial velocity vector of the projectile points in this direction like so, along the same direction as R0 monkey. Okay, so right here is that initial velocity vector of the projectile. This right here in red is V0 projectile. The initial speed of the projectile, by the way, the magnitude of this velocity vector, that's determined by how hard I blow into the blowgun. Okay, and then the two objects collide. Let's say that the two objects collide right here. The projectile does like so. Okay, now how high above the floor the two objects collide with each other is determined by, very simply, how hard I blow into the blowgun. Now, we don't know, of course, what the final position of the two objects is. It's determined, as I said, by how hard I blow into the blowgun. But we do know on this diagram that right here, the final position vector r of both objects is the same. The reason for that is because the two objects collide. Okay, and then we have the acceleration vectors. We of course already know what the acceleration of the monkey is from chapter 2. It's just in one-dimensional free fall. Its acceleration is downwards at 9.8 meters per second squared. So the acceleration of the monkey is known. That's minus g j hat. Okay, the unknown in all of this, what we're trying to find, is the acceleration of the projectile. Like so. Okay, now how do I proceed? Well, what I'm going to do first of all is just write down the position equation r here for constant acceleration. It's the same equation that we saw back in chapter 2 for one-dimensional cases. Here's how we would write this out, however, for this two-dimensional case. Final position rather equals initial position plus initial velocity times time plus 1/2 times the acceleration times t squared. It's the same expression that we saw back in chapter 2 for one-dimensional cases, now written out here for this two-dimensional case. What I'm going to do is write this equation for the two objects and then set the two equations equal to each other. I'll set them equal to each other because remember that both objects have the same final position r at the end of the demonstration when the two objects collide. Okay, so first of all for the monkey. So the final position of the monkey is equal to its initial position, r naught monkey, plus its initial velocity times time, but that's 0 for the monkey, plus 1/2 times the acceleration of the monkey times t squared. Okay, and then they have the position vector r for the projectile. So we first of all have r naught for the projectile, which is 0, plus v naught projectile times time, plus that are unknown, 1/2 times the acceleration of the projectile times t squared, like so. And now let's just set the two equations equal to each other and see what happens. I'm going to do so by writing the unknown, that is for the projectile, on the left-hand side. Okay, so we have now for the projectile, v naught projectile times t plus 1/2 times the acceleration of the projectile, t squared, equals then for the monkey, r naught monkey, and then plus 1/2 times the acceleration of the monkey times t squared, like so. Okay, so once again, I'm just writing down the position equation for each object and now setting them equal to each other. So what do I do from here? Well, take a look at this quantity right here. This quantity right here, v naught projectile times time t, is the following. It's the red initial velocity vector here of the projectile multiplied by t. And then take a look at this quantity right here. R naught monkey is just this distance right here. What could you say about these two terms? These two terms are equal to each other. The reason why they're equal to each other is as follows. Imagine what would happen if there was no acceleration. If there was no acceleration, the monkey would just sit here. And then in time t, the projectile would move at a constant velocity and then hit the target like so. In other words, it would travel that distance, r naught monkey, in time t. So then therefore, the two expressions, here and here, they're equal to each other. They cancel each other out for that reason. And then take a look at the result that is left. The result that is left is probably what some of you suspected when I initially posed the question earlier about what the acceleration of the projectile is going to equal. Well, we now have this term here equal to this term here. Notice that the 1/2 t squareds cancel. 1/2 here, and t squared here and here. And then here is the result. Therefore, the acceleration of the projectile is the same as the acceleration of the monkey. It's just downwards at 9.8 meters per second squared. In other words, a projectile is also in free fall. You can think of this result of this demonstration in the following way. It's the same Earth. There is nothing different about the Earth's gravity if you're talking about the one-dimensional case of the object in free fall, like in chapter 2, the monkey, like so, or now the two-dimensional case of an object as a projectile moving in two-dimensional space, like so. In both cases, it's still the same Earth. It's still the same gravity. Therefore, the acceleration is downwards, at 9.8 meters per second squared. Another way to think of this demonstration is that each of the objects is falling. Each object is falling below a line that it would have traveled if there was no acceleration. For example, in the case of the monkey, if the monkey didn't accelerate, it would sit there on the ceiling at its initial point. But it is accelerating. It's falling below that point as it falls under the influence of the Earth's gravity. The projectile is doing the same thing. In this case, the projectile is falling below a line. It's specifically falling below this line, like so, that it would have traveled if there was no acceleration. The acceleration of the projectile is also downwards at 9.8 meters per second squared. A couple of other details here about this demonstration. I've been describing the demonstration here on the board as a two-dimensional type of motion, but of course the projectile itself is moving in the three-dimensional space of this room during the demonstration. Is it then, therefore, a truly three-dimensional type of motion as opposed to a two-dimensional type of motion? No, it's two-dimensional for the following reason. Because a projectile's acceleration is downwards at 9.8 meters per second squared, this then means that the velocity component of a projectile horizontally never changes. So then, therefore, on the board, in the z direction, what is the initial velocity of the projectile? It's zero. It's zero by definition in the demonstration because by definition, V0 projectile is fired into the xy plane. So the z component of the velocity vector of the projectile is zero. But this is a horizontal direction and there's no acceleration horizontally. So then therefore the velocity in this direction, the z direction of the projectile, is always equal to zero. This then means that it truly is a two-dimensional type of motion, not a three-dimensional type of motion. That is, the projectile itself moves into a plane. Another way to think about the demonstration is as follows. Let's say that I just fire the gun with enough force, if you will, such that the projectile just barely falls out of the barrel of the gun and then immediately starts to fall to the floor. Will it still eventually hit the target if the floor was not in the way? Yes, it would. It would eventually hit the target somewhere way below the floor itself, but it would still hit the target because there's no acceleration horizontally for a projectile. So now we've concluded here with the successful demonstration that the acceleration of a projectile is downwards at 9.8 meters per second squared. This then means that we can easily describe the kinematics of a projectile. I'll get to that in part 2 of this lecture.